Hello, I'm Doug Smith, and this is Layout Analysis Areas of Improvement. Layout analysis is a quick and efficient design method, but it is not without its drawbacks. It is not very good for complex interfaces, and it lacks reliability and validity. No provisions are made for either error or cognitive analysis, nor is task performance time considered. First, we look at complexity. As the size and complexity of an interface grows, layout analysis becomes increasingly difficult to apply. The process grinds to a halt as the designer must visually track a number of elements. Also, with an expanding interface, there become exponentially more solutions, each of which the designer must evaluate. Here's an example of an automotive interface redesigned with layout analysis versus a very complex aircraft interface, where layout analysis would be difficult to use. Layout analysis is a somewhat subjective method. From this subjectivity comes a lack of consistency. Different designers may have differing definitions of a good design. This makes layout analysis unreliable and hard to validate. A group of researchers attempted to solve this issue by iteratively considering ergonomic principles and consulting with subject matter experts who applied design heuristics to layout analysis. Layout analysis also fails to consider human error. The aforementioned attempt to improve reliability comes close, implicitly considering error by highlighting interference as a potential issue. Error prevention was also one of the areas which the heuristic evaluation attacked. Another study suggested using layout analysis to prevent errors identified through specialized error analysis methods. Cognitive task analysis and mental workload analysis are omitted from layout analysis. One could say that cognitive analysis is inherent in layout analysis, in the way a designer forms groups and redesigns the interface, but there is no formal assessment. Any related considerations would be subjective to the interface designer suffering from the issues mentioned earlier. Finally, layout analysis does not consider task performance time. The functional groupings are intended to increase speed, but there is no formal baseline by which to measure performance time. One study suggested recording reaction time if this is important, but this is a slightly different concept than task performance time. Once again, there is no formal incorporation of this into layout analysis. So how do we improve layout analysis? In practice, layout analysis is informally augmented. It is commonly used in conjunction with other methods, but we need something more integral to the method. Improvements using the strengths of layout analysis would be the most useful. Trying to improve on complexity applications, for example, might not be useful, as either layout analysis would need to be further complicated or a complex interface simplified to obscurity. We should then use something that is fairly simple, early phase, and high level. The method proposed in this presentation attempts to include error analysis in layout analysis. By taking error types from classic error analysis methods and distilling them into simple, high-level concepts, we get three error types: temporal or timing-related errors, spatial or object and positional-related errors, and cognitive or comprehension-related errors. Taking these error types, we can then apply a few design considerations. The factors considered here are density, uniformity, and overloading. Density is the number of elements in a given region, especially compared to their respective sizes. Uniformity is how alike elements are, whether this be shape or color, or more significant properties like element type or height in interfaces where height is a factor. Overloading is the act of assigning multiple functions or tasks to a single element or region. The proposal here is to map the quality of these design factors to error evaluations using a logistic function. The resultant function is called the layout error analysis function. The logistic function used as its basis is used in a wide variety of fields to model both natural and artificial processes that vary between 0 and some fixed value. In order to modify this function for our purposes, we take note that the function saturates at plus or minus 6. We set kx sub 0 equal to 6 to center the function in positive x values, then set k equals to 12 to normalize the function on the x-axis. Setting L equals to 1 does the same on the y-axis. Multiplying x by a coefficient, our new k, allows for the function to be shaped while anchoring it at the origin. We now have a function that varies from 0 to 1 on the y-axis, which is called the error rating, and 0 to 1 on the x-axis for the same range. The x-axis is the quality value and is a measure of the effect density, uniformity, or overloading could have on temporal, spatial, or cognitive errors. Each full assessment will provide 9 values which can be summed to gain a more complete picture. This function can be applied either to individual groups or the entire interface, though a group-wise application may encounter complexity issues. Thank you for your time. I'm Doug Smith, and this has been Layout Analysis Areas of Improvement.